Hello everyone, and welcome to today's Chem lesson. Today we're going to talk a little bit more about solutions, specifically into how we differentiate between something with a teeny bit of solute in it and something with a lot of solute in it, and all the things in between. Imagine for a second that you have two identical cups of water. In this first cup of water, we are going to put a single grain of salt. And that grain of salt will dissolve in this water, and we will have created salt water. Imagine in this second cup of water, we take a big pile of salt, and we put that whole pile of salt into this water. And that salt dissolves, and we have created salt water. These two cups of salt water are not the same, but they end up with the same name. They both end up being called salt water. And we know from the past that we don't want that. Right? We hate it when two different things have the same name in chemistry. We want a way to be able to talk about this left cup of salt water and know that it is different from this right cup of salt water. And the way we're going to do that is by using these terms here. It's unsaturated, saturated, supersaturated, and saturated with extra. They're going to help us tell the difference between these two different cups of salt water that both have the name salt water. Let's look at these terms visually, because I think that's the easiest way to go about understanding them. Here, we see four identical cups of water. You can tell that they are cups of water because they are cylinders and they are blue. And that's about as good as art as I can make. These are all identical cups of water except for the contents inside, right? You'll notice there are different amounts of dissolved molecules in these cups of water. We're going to start with this one here. This cup is a saturated cup of water with orange, right? It's saturated with orange, full of orange. A saturated solution is when the solvent, the water in this case, is holding the maximum amount of solute. And in this case, that's these orange dissolved molecules. Because it is saturated, it is holding the maximum. Right? I chose, when I made this slide, that 4 orange balls would be saturated for this cup. Anything less than 4 would be unsaturated. Right, this cup holding 2 orange balls here, 2 orange molecules, is an unsaturated cup of water. It is not holding the maximum amount of solute. Right? We know that that is 4. A supersaturated solution is when the solvent is holding more than the maximum. Right? So that's anything 5 or higher for this diagram. And lastly, we have saturated with extra. And that occurs when the maximum amount of solute is being held. Right here we've got 4 dissolved, but we also have some on the bottom. Right, this means that when you're looking at this, you see some of this powder on the bottom of your cup. These four terms, these four words are going to help us differentiate between the different types of solutions that exist. Right. Saturated means the same thing in chemistry as it does in English. When we talk about a saturated fat, we're talking about a fat that is full of hydrogen. When we talk about a sponge that is saturated with water, we're talking about a sponge that is full of water. Right? To be saturated is to be filled. Right? And so that is the same definition as we're seeing here in chemistry. A saturated solution is full, holding the maximum amount of solute that it can hold. But Mr. M, you say, if 4 is the maximum, how is supersaturated holding 6? Supersaturated is a very special, very rare situation. You can get something to be supersaturated, but it takes a lot of patience and a lot of care to get things in just the right conditions for them to dissolve more than the normal. Most of the time, you go straight from saturated to saturated with extra. Right? Normally, if I put a 5th orange ball in here, it'll just sink to the bottom and not dissolve. It is possible, like I said, it's possible to get super saturated, to have the conditions just right, to be moving just slowly enough that everything is balanced out. But any change will knock those extras out of solution and onto the bottom here. All right, think of it like a house of cards. Easy to build the first layer, right, which would make us saturated, but once you go and start adding the second and third and fourth layers, you risk knocking the whole thing over and getting to saturated with extra. That's not to say that supersaturated solutions don't exist. Honey, right, the honey you have in your cabinets at home, is a supersaturated solution. It is sugar dissolved in water, but dissolved so perfectly that it creates this supersaturated solution. You'll notice that it's really easy for honey to solidify, right? You end up with like crusty sugar on the bottom of your honey container if you leave it alone for too long or if you don't use it often enough. It's really easy to go from honey to crystallized sugar and sugar water. Now, my question to you is, if we look at these diagrams, these are all dealing with these orange molecules. What if I drew in these little red molecules instead? Right? If I take these out and I put in little red molecules, are those going to have the same proportions as the orange ones did? Are 4 little red molecules going to be saturated for this amount of water? Can you tell? Right. These little red molecules are smaller than the orange ones. Does that matter when I'm looking at saturated versus unsaturated versus supersaturated? Is this amount of water going to hold 4 of these littler red ones, or can it hold more without going over? And the answer to that question is you can't really tell. These numbers that we have here work for these orange molecules, and only these orange molecules. If we change molecules, Maybe it holds more, maybe it holds less. We can't tell. That's why we have a piece of the reference table that's going to help us determine when something is saturated, supersaturated, unsaturated, or saturated with extra. And that piece of the reference table is table G. Here we have table G in all of its glory, and it is a little more intimidating at first glance. But as we learn and as we see this, we actually know that this isn't a very intimidating table. At any time, we are going to be looking at just one of these bold lines and pretending the others don't exist. All right, let's look at NH4Cl together. That is this line right here. Try to trace it as best as I can. Not bad. All right, that is the bold line for NH4Cl. So when we're talking about NH4Cl, we're going to look at this line only and pretend the other ones don't exist. Any value below the line is unsaturated. So that means all of the points here, all of these points here are unsaturated for NH4Cl. All right, everything that falls below this line. Any value above the line is either supersaturated or saturated with extra. So that means all of these points up here, everything above this line, is going to be saturated, supersaturated, or saturated with extra. And any value on the line itself is saturated. So any intersection of this line shows you a saturated solution. All right, so when we look at a question, all right, like this example down here, how much ammonium chloride would we need to saturate 100 milliliters of water at 70 degrees Celsius? I know ammonium chloride is NH4Cl, so I'm looking at this line. I want it to be saturated, so I want it to be on the line. So I'm going to get rid of the purple and the blue here. I see 70 degrees Celsius, so I'm looking here. And I want to see where this intersection is. All right, and I'm going to read this across with the best straight line I can muster. And I see that that would be 62 grams. Now you're saying, and I hear you, all right, Mr. M, you boxed off 100 milliliters of water but didn't do anything with it. Right? Ammonium chloride told you which line to focus on. Saturated told you it needed to be on the line. 70 degrees Celsius was your x-axis point. And they asked you for grams, so that was your y-axis point. So what's this 100 milliliters of water for? The 100 milliliters of water is there specifically because of this little bit on the scale for the y-axis. The y-axis, these numbers are grams of solute for every 100 milliliters of water. So this 100 milliliters of water just tells me I need to use this scale as given. And it's just a little confirmation piece. If it had said 200 milliliters of water, then I would have needed to adjust my numbers. If it had said 50 milliliters of water, I would have needed to adjust these numbers. Right? I would have needed to adjust my y-axis appropriately. If it was 200 milliliters of water, I doubled my denominator. I must also double all of these values. So instead of 100, this would have been 200. This would have been 120. This would have been 80, so on and so forth. If they had given me 50 milliliters of water, I would have needed to cut all of these numbers in half. Right? I cut my denominator in half, and I need everything to remain proportional, so the rest must be cut in half. This would have been 10, 15, 20, 30, etc. But the 100 milliliters of water is just there to show you that you're using the y-axis as written. Let's take a look at some practice problems. I'm leaving table G up for us. At what temperature is a solution of 52 grams of HCl in 100 milliliters of water saturated? So, what do they give me here? They give me at what temperature? They give me 52 grams. They give me HCl. They give me 100 milliliters of water. They give me saturated. All right, let's take that piece by piece. 52 grams means we're right here on the y-axis. HCl means we're looking at this line. 100 milliliters of water means we're using the y-axis as given. And saturated means we're looking on the line itself. So we want this 52 to intersect with the HCl line. And we want to follow that down to get our temperature, which will be 70 degrees Celsius. What about this one? You make a solution of ammonia, NH3, using 50 grams of solute and 100 grams of solvent. At what temperature is the solution saturated? Here, let's look at what they give us. They give us ammonia, NH3. That is this line here. They give us 50 grams of solute. That's right here. 100 grams of solvent means we're just using this y-axis as written. Saturated means we want it to intersect on the line. And they want to know what temperature that is. And so we're going to follow that down. somewhere between 20 and 30, so definitely not 20, definitely not 30. It's going to end up as 25. What about this one? You make a solution of sodium nitrate, which is NaNO3, at 35 degrees Celsius using 100 grams of water and 200 grams of solvent. Is the solution saturated? Here the answer is actually no. This is not a saturated solution. And let's look at why. It comes from this piece of information right here. Let's look at the information that they gave us. Sodium nitrate is NaNO3. 35 degrees Celsius is right here. 100 grams of solute and 200 grams of solvent. 200 grams of solvent is double what the y-axis is giving us. So if this got doubled, then all of these numbers need to get doubled as well. And our actual 100 point is right here. So the actual intersection of 35 degrees Celsius and 100 grams of sodium nitrate in 200 grams of solvent is right here. Is this value above, below, or on this line? It is very clearly below the line, making it unsaturated. Normally, if this had said 100 grams of solvent, then we would have used the y-axis as written, and this would have been a yes. But when we double the water, we need twice as much solvent, or solute, to fill that solvent. So these numbers need to adjust accordingly. One more practice problem to wrap us up for the day, and this one comes directly off of an old Regents exam. According to this reference table, which compound's solubility decreases most rapidly as the temperature changes from 10 to 70 degrees Celsius? This question is a little bit different from the others that we looked at. They're not looking for a particular intersection, right? They're just asking you to look at the general trend. And here the correct answer is 2. When we look at this very clearly, NH4Cl goes up, so that's not decreasing. HCl goes down. KCl goes up. So we're looking at NH3, which also goes down. NH3 and HCl. And when we look from 10 to 70, this is the more rapid decline. Now, that does strike me as strange, though, right? Why do these lines, why do they go down while every other line goes up? What's different about these 3 things when we compare it to everything else on the table? These 3 compounds are actually gases, while everything else on the table is a solid. And that is going to affect why these go up and the others go down. And that's going to be our whole discussion next time. For now, I'm going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.